Okay, so let's complete this section where we're creating this single phase generator, and we'll walk it through a cycle. We'll look at what's happening physically, and we'll also look at graphical interpretation of what is happening physically. So again, here's our basic generator that we're going to use to demonstrate a single phase generator. And what we have is a conductor here. It runs the length of that, comes around the other side and terminates here, rotating magnetic field, inducing a voltage in that coil that's equal to this, which is an instantaneous voltage. This is the flux density in Tesla. This is the length of that conductor that's exposed to the field. That would be the sum of both of those sides. And then the velocity is the peripheral speed in meters per second. So what we're going to get here, we're going to get the sum of all the voltages that are induced in all the conductors in the terminal. And so this total voltage here, and he has a specific equation that is matched to our designation, where we call this voltage EA1. It's going to reach a maximum when the poles are in the position shown here. And the reason for that is it's because the most flux occurs in this position. So based on this equation, everything else being equal, the greatest voltage is going to be at that point. On the other hand, if we look at 8.2, and we think about the flux that's coming from this rotating magnet. And at this point, we're going to say that according to this equation here, that the flux density is going to be, for all extents, 0. So at this point, as it's rotated 90 degrees from this point, that the voltage induced in that conductor is going to be 0. Okay, so what we're doing, we're rotating this magnetic field around clockwise. It could have been counterclockwise as well. Only thing that would change, the polarities would change. But anyway, so as we rotate this around, what we end up with is a sinusoidal waveform that is generated across that coil that looks like this if we were to graph it. And if you look at this closely, not sure how clearly this is on your screen there, but that says EA1. Okay, so if we looked at this point where the voltage is the maximum, of course we're talking about physically what's happening here. And then if we look at this point, 0, what we're looking at is here when the magnetic flux is not cutting the conductor at all. All right, and then so this thing continues to rotate, and we have a positive peak, and then we're going to have a negative peak after 180 degrees. Again, the only thing changing is the polarity. And if we're talking about current, the direction of the current would change. Also, another 0 point here after another rotation of 90 degrees, coming back to a full cycle there where we're back to the original point. And he says, okay, let's say this is, based on this equation, and we're this peaks at 20 volts here, and he's showing us that. So this would be positive 20, this would be negative 20, this would be, positive 20 here, and it rotates through this sinusoidal waveform. And in a machine that does this is called an AC generator, for obvious reasons, right? It's generating an AC voltage. Sometimes you'll hear it called a synchronous generator. We won't get into that right now. And this particular machine is called a single phase generator because like he says in the book, it's just one phase of electricity. And, so, that's what we get from this. And all we're going to do is we're going to build on this single phase generator, and we're going to build on that and create a 3-phase generator with some of these same ideas. Okay, So rotating through, physically here, electrically graphed here from the output of the voltage across that coil, this is what we'd be looking at.